Hey guys, it's Alex from Canyon Academy, and today we're going to go all over Sn1 and E1, from their kinetics to mechanism and a lot of stuff in between. First off, I'm going to go over their steps. This is how your book highlights it, just oversimplified. So first you have your leaving group leaving, making a carbocation, and I will help you make this step more lively by illustrating it with this graph here. And remember, your rules of electron and your of arrow drawing of your electrons are the parts that you are showing being moved. So it's always great to identify your parts of the reaction first, such as your leaving group right away, making sure it's a good leaving group, and the halogens except fluoride are pretty good. Next, we would look at our reagents and see if we have a good nucleophile, actually a weak nucleophile for this case, and those usually are any carbon with an alcohol group, and sometimes you see water as well. Those are the two very common ones. So let's say this carbon here is just a ethyl group, so CH3, CH2. Okay, so that is a weak nucleophile. Now, as we said, the first step is our leaving group leaves. So we draw this arrow out because its electrons are going with it. So the first step is simply making that go away. And since we created a charge, we also have to make sure that our charges account for that. So if we make a negative, that means we have a positive now because we started off neutral. So now we have this compound here. Our leaving group was up there. So now it's replaced with a positive charge, and the leaving group is off on its way, being stable on its own, like a good leaving group does. Next, let's look at our mechanisms. Now, the next is optional. This only happens if possible. It's a rearrangement, and this happens if a carbocation sees that it can be at a more stable position. Now there's two types. You can have a hydrogen moving to make this possible, or a methyl group moving. Methyl would take a little bit more energy, but is also worth it at times for a more stable reaction. So at this stage, if we look at our diagram, the tops being transition states of the step and the bottom being the intermediates. This step right here is your intermediate, so it's at the bottom of the hill before the second stage happens. And that's where we are right now here. This is our intermediate, and the transition state would be a little dash. It would look like this with a little dash line instead of this bond here as it's starting to leave. It's good to know exactly what this energy diagram looks like. It's important to note as well that for every step you have an intermediate. So as I drew out these steps, you can have up to 4 hills on an Sn1 reaction and up to 3 hills on an E1 reaction. So rearrange. Let's go over what it looks like. So we're here, and we have the option of shifting a hydrogen to that position or a methyl group. So to our left, it usually has to be a hydrogen really close nearby. We call them beta hydrogens because here's your alpha carbon. It's the carbon attached to that carbocation, and it has alpha hydrogens. In this case, it has 1 and that positive charge. But no point of shifting that guy because that carbon already has 1. So this is your alpha carbon here, and we can look at our beta carbons, which are the carbons attached to this carbon here. So here we have a beta, and here we have a beta. This one on beta on the left has a hydrogen. This beta on the right does not. However, we could also do a methyl shift since that beta has plenty of methyl groups too. So you could have either this H donating its electrons to that positive charge, or its methyl group, this C bond donating its electrons to this. Which one's going to happen though? more likely you're going to have the hydrogen doing this because it takes less energy for a hydrogen to move its whole electron than this giant methyl to. But both are possible. When you would see a methyl shift is when, let's say this wasn't a hydrogen, if this was a methyl group as well, and you had no option of making a hydrogen shift. If you're choosing between a methyl and a methyl, it doesn't matter, you can get both. But let's go back to our example where we have H's. So H will take less energy, so we're not going to have to move this big carbon. So it's going to donate both its electrons, so remember each bond here represents 2 electrons, to that H, and you're going to get this funky rearrangement. So let's redraw our bond. One sec. So we move the H from this spot over here to this spot. And we still originally had another H there because you had this H and a positive charge. Now, since we moved that electrons there, where did the positive charge end up? It takes the place of that old hydrogen. Hence, we have a rearrangement because it went over to the next side. This is much more stable because a tertiary carbocation is more stable than a secondary carbocation, and that's why you have this rearrangement. Here you have your secondary carbocation because it's attached to 2 carbons. It's attached to this one and this one. But now we're at a much more stable one, this tertiary carbocation, because it's attached to 1, 2, 3 carbons, which is much better off than where it was before. And I'll explain more of that in my other video about carbocations. Now, that is another step. So it's another spot on our energy diagram. It's optional, so it's out here in red. And I'll highlight it in red as well. It's that hill right there. And this one won't happen all the time because sometimes you don't have an option of going to rearrange. Sometimes you have ethyl groups all around, no methyl or hydrogen. And sometimes you're already in a really stable spot, so there's no point of rearranging. You're already in the best spot possible. So this peak won't always show up. Now, on to the next stage. Now that we have this other carbocation intermediate, not as important as the first. So we rearranged. Now we go into our Sn1 specific steps. Our step 3 is our nucleophile attacks the carbocation. So we already identified our nucleophile. It's still over here, just waiting around to get its turn. Here we have our weak nucleophile, and now it gets to attack the positive charge, the carbocation. So we can draw this step out and see what it's going to look like. I'm just going to drag and drop. The only difference is now you have this big ethanol attached to it, and it still has it connected to the same stuff, except now it's connected to where that positive charge was. So here we have our ethyl group. This is our nucleophile. So this is where it is now. All that was our nucleophile until it attached. It's good to note that now the oxygen is positively charged because it has 3 bonds and 1 lone pair. Because that lone pair here is what actually attacked that positive charge in the carbocation. Now, of course, we're still not done, but let's look at our next stage in the energy diagram, and you have the second molehill, 3 being the transition state on top, and the bottom 3 is our product or intermediate actually of this step. So intermediate in this case is this with the positive charge in the H, now attached to where the carbocation was. Next, we shall talk about the last stage, which is also optional, deprotonate if you are able or if it's even possible. And this would also be another hill, which is a very common mistake. We often forget the energy diagram has two optional hills, so we always have to be good at our mechanism. So now we do have the option to deprotonate. Now, when do you deprotonate? When you have a positively charged on the nucleophile and it had because of this hydrogen. So if you had water and it was attached to this now, it would also be positively charged. So now we have to take off this hydrogen. Good way to do it. You can just draw, if you like, the H leaving on its own, but it's usually better. Actually, it'd be the other way around. Sorry. This would keep its electrons because that would neutralize the positive charge. Always remember that you go towards the positive charge. So the negative electrons from the hydrogen will go towards the positive. Now, what's taking the hydrogen? You could technically have this on its own, but we usually like drawing out another. Let's say we had excess. We don't just have 1 mole of our nucleophile. That can end up taking that hydrogen and allowing it to donate its electrons. So what you would have is, let me draw this out from the last step. And it's the same, except we got rid of a proton. We deprotonated. Oops. Sorry about that. Okay, so we have the O and the ethyl group. I'll just draw ET. It's good to note ET just means your ethyl, so it's CH3, CH2. You'll see that drawn that way a couple times along with methyl groups. And that there is our product. So we can look out and see if we completed our steps. We deprotonated. This would be, again, the last bump. And now we're at our product, which is 0.4 here. Okay, on to E1. E1 is about the same. You still have the same first and second step, but we have now this new third step where the nucleophile attacks a beta hydrogen, and that hydrogen then donates its electrons towards the carbocation, of course, because we go negative to positive. Here you only have one optional molehill, and that's just the rearrangement. So let's go over to this. This is a very common problem here. Now let's get to identifying. Always a great start. The thing on this problem is OH is not a great leaving group. On its own, that's an ugly charge with nothing to stabilize it. If it's unstable on its own, it's not a good leaving group. We also don't have a nucleophile, really. We have water, which could be a nucleophile, but it doesn't have a leaving group to act on. But we do have this proton, and we have this slightly basic alcohol. So we can actually do an acid-base reaction. So we do this, and we end up making water. Now, why do we do this step first? Because we do not have the essentials to actually make a reaction that we know of. So we add that H to this, and this would have to be concentrated to make this reaction actually go. And now we have a water molecule attached to this. Now the thing about water, when it's attached to one of our carbons here, is now it's a good leaving group. Water is a really good leaving group because it's slightly basic, and when it leaves, it's very stable on its own, which is basically the two principles of what defines a leaving group. Water is extremely stable on its own. Now, the thing is, where is our nucleophile? We could use this water here, but sometimes you won't even be given this water up there, which is also interesting because water isn't just a leaving group, it's also a good nucleophile. It's a weak one, but it's also can be used in our reaction here. So let me copy this carbon skeleton for us for the next step that actually begins the E1 mechanism itself. That's our leaving group leaving, remember? So we're off to our actual mechanism. Our leaving group leaves, which looks like it's taking the electrons with it. So you end up with your original carbon skeleton, which is a carbocation. Remember, this is your rate determining step, plus your water molecule, your leaving group that you made. Now, looks kind of funny, doesn't it? Because now you don't have a reagent if we ignored the water up above, if that wasn't there, because sometimes that won't be given to you. Well, the thing is, since water is also a good nucleophile, we can actually make it facilitate the E1 mechanism. So the next step is, of course, rearrange if possible. Now let's look if that is an option here. So let's identify our alpha carbon. That's the one with the positive charge. This is our alpha. And then our two betas here and here. So this beta carbon up here is a primary, and this one over here is a secondary, while our original was secondary. So it doesn't have any really good options. It can go to that secondary and break even, but why waste all that extra energy if you're going to end up the same? And plus, this is also identical. It's a mirror image of each other, so there's not really, it wouldn't really give you a different product either. It would just be flipped over and then react to do the same thing. So no point of rearranging in this case. So in this case, you wouldn't see this molehill here. It would just be these two. But you'd have that intermediate still, which is still the carbocation. But of course, if it was an option, we would have, if we had the option to go to a more stable carbocation. So in this case, we decided that we're not going to rearrange because there's no point. But on to stage 3, nucleophile attacks a beta hydrogen, and hydrogen then donates its electrons. Okay, so water now can attack either one of these beta hydrogens. So we can attack this hydrogen here, or these hydrogens here. So a couple of factors onto which one it'll attack. You can technically do either. You'll definitely get a mix of both. So let's draw out that mechanism. It's electrons from this water attack the beta hydrogen. Then this donates its electrons towards the cation. And there's your mechanism. Let's draw out what that makes. This goes, it's important to note that this arrow is going towards that bond, making a double bond. Of course, eliminations always make double bonds, while substitutions always add stuff. So our new step here is we added this double bond here. But we can also technically take this hydrogen here on the other side. So let's draw what that one looks like. You can also have it take this and this donate its electrons towards the carbocation. So another different product we can have is a double bond here. Now the question becomes, which ones are you going to have more of? Which is the major contributor? It'd be useful to know the stability of these. You will usually get a product that's more stable. Now, which one of these is more stable? It's the more substituted alkene. So I know what that means. Let's identify the alpha carbons on this alkene. That's the ones connected to the double bond. So this one's connected to that double bond. This one's connected to it. Now you count how many beta carbons are around that. I'm going to do them in blue. So you have one next to this alpha and one next to this alpha. Here you have one next to this, and this one over here is too far, so it's not a beta. So this one has 1, so this is technically a primary, and this is a secondary. Secondary alkenes are more stable than primary, so what you end up having is this being your major product. You would also, it's good to note, have a little of Sn1 product. So if you drew that out, you would go back to the beginning, because the problem with Sn1 and Sn1 and E1 is that their products are really hard to pick out, since they're going to be a bunch of mixtures. So you don't really use them for synthesis very often, since sometimes you're going to get like 60% of one, 20% of another. We sometimes focus much more on E2 and Sn2, since they're much more useful for synthesis problems. Okay, last thing for us is to go over the kinetics of this. This formula here is given by this formula here. The rate of the reaction, R, is equal to the rate constant times the concentration is this arrow here, of the compound with the leaving group. Sometimes you just see this in your notebook as Rx, because halogens are usually good leaving groups. So what this means is that your rate determining step, we said, was the carbocation, right? So what this means is the whole reaction depends on how much of this, let's say this is actually your leaving group here, how much of your Rx, so this is how much of your Rx you have. X is your leaving group, so that's this water molecule in this case, and R is all of the carbon skeleton. It's all dependent on how much of this you have times a constant. That's because it's determined by how much of the carbocation you make, because this takes so long. Because this is not really that much more stable than the original molecule. So it's a very slow reaction, so it basically only depends on that first step, like most reactions that we learn do as well. Really easy, because it only really as long as you know what the rate determining step is, definitely something you need to know. Alright guys, that's it for Sn1 and E1.